Okay, hey everyone, how's everyone doing today? Hope everything's okay. Today I'll be doing the week 8 physics CA quiz. So I'll start with question 1. Very easy. We took this in grade 6. Which of the following statements describes the do's and don'ts of electricity are true? Okay, obviously don't switch off all devices and disconnect all devices when you're not using them is wrong because you're supposed to switch off all devices, right? When you're not using them. Do replace fuse wire with the correct rating wire, never with ordinary wire, obviously, just in case any emergencies may occur, any earthing issues or any overcurrent. You have to replace it with the correct rating and not just any random wire here. Do learn how to connect plugs correctly, obviously, and do not expose any wiring even though it's connected to a socket. This is especially dangerous because, again, if you touch it, you will get electrocuted, or anything around it will get electrocuted, leading to fires or shorts. Never use plugs which are damaged and have no cable grip. Yes, definitely, because if they are damaged, they might lead to very hazardous things that are very dangerous. Okay, question 2. A rectangular wire ABCD is connected to a galvanometer that measures induced EMF. The wire is rotated at a constant rate inside the horseshoe magnet as shown below. How can we increase the induced EMF? Okay, so here obviously the options were very dumb, right? It was like flip the magnet or something like that, and then there were two options that I think some people fell for in the AMS because this came in a CA quiz previously, and I think it came in an actual exam. First of all, they said use a more sensitive galvanometer or rotate the wire faster, which is the correct answer. Right? Now, why don't you use a more sensitive galvanometer? The more sensitive galvanometer, this isn't for this. This isn't for the induced EMF. The more sensitive galvanometer is when you're passing a magnet or something through the galvanometer itself. And even then, again, a galvanometer is just a measuring device. So why would using a more sensitive one lead to more EMF? It's a measuring tool. It's like saying using a more sensitive ammeter gives me more current. That doesn't work. That's just measuring more accurately. Okay. Describe how an alternating current is induced. A loop ABCD is rotating between the poles of a permanent magnet. Which of the following statements are true? Okay, when ABCD is horizontal, the rate of flux change through the loop is 0. Now, this is when it's horizontal, right? This is relatively when it's horizontal. This is our magnetic field. Okay, it's like this. It's going from north to south. Here, the flux is maximum. The flux itself is the maximum it can get, right? But the flux change, okay, which is phi, is actually 0, right? It is equal to 0. So this is correct. When ABCD is vertical, the current through the loop is 0. No, because it doesn't make sense to do that. No, we just said when it's horizontal, you have maximum flux. So the point doesn't really correlate. بس يعني, so this is wrong. The current generated in ABCD is called an alternating current. Yes, this is called an alternating current. It's an AC current because you're rotating, right? And this is cutting through the magnetic field, and the magnetic field is continuously changing. Like, for example, this is our magnet, right? It's gonna draw it like this. And so initially it was this. Initially it was this wrong. But then you changed it to be vertical. And then you changed it to be horizontal again, and then vertical again. You're alternating, hence inducing an alternating current. So yes, the current is an alternating current. The current through the galvanometer changes its direction twice every complete rotation. Yes, because, as I said, originally it was horizontal, right? Imagine this is horizontal, this place here. Okay, then it's changing to being vertical, right? So wait, you're rotating. Actually, let me replace it with letters. So it was initially horizontal, then it's vertical. You're flipping it 90 degrees, then you're flipping it 90 degrees again, which is making it horizontal again, and then vertical, and then the cycle repeats, right? So as you can see, there are two verticals and two horizontals, meaning that the current changes its direction, right? Because it is already changing its direction anyway. Now, the frequency of the generated current is double the frequency of the loop's rotation. This has nothing to do with any of this, and we don't even know if this is true or not, so this is incorrect. Okay, so those are the answers. I think I skipped a question. Sound can be defined as a longitudinal wave motion, and since it is mechanical, it needs a medium to travel through. Now, there are two types of waves. They have electromagnetic or mechanical. Sound is a mechanical wave. Okay, now mechanical waves can be longitudinal or transverse. Okay, Longitudinal, the vibration of the particles is in the same direction as the propagation of energy. You will see this definition later, and I will clarify more on it when the question comes, because this did come up. So I don't want to complicate it now and confuse you. No, I'm gonna have the school's definition on it, and then I'm gonna add to it. For now, just memorize that sound is longitudinal, and it is mechanical. Okay, and mechanical waves need a medium to travel through always. The medium in a mechanical wave is determining its speed and how it travels always. So the sound wave or any mechanical wave will need mediums to travel through them. Okay. A pulse in a rope reaches its end, which is free to move up and down a pole. Okay, since it is a free moving pole, it's a free end. What will happen to the pulse upon reflection? The frequency will remain the same. Okay? The amplitude of the pulse remains practically the same as well, right? Because you're not changing it. You're simply just, I'll explain it now. So, this can be explained with this drawing. Okay, we have a free end. This is a free end. Right? So, when this hits, right? Imagine this traveling. It travels along. Okay? Then this can either move down or up, doesn't matter. I'm gonna say it moves down. This is the same free end, and then it's gonna travel the exact same path, just in the opposite direction, and with the same properties. This here, this amplitude is the same as this amplitude. It doesn't look like it because my drawing's bad, but the amplitudes are the same because it's a free end, and the frequency is the same. It's the exact same pulse, except it's traveling in the opposite direction. Now, suppose this was not a free end. Okay, this isn't a free end. It's stuck, it's close to this wall. What it will do, like this, same frequency, same amplitude, but it's inverted. So the pulse will be inverted. If it's a closed end, or whatever you call it, I don't know what you call it, but this option would be correct if it wasn't free end. Keep this in mind, because they might ask it. Okay, question 6. Why is an AC powered? Let me read the question. An ideal transformer is connected to a 240 volt 50 hertz supply. The primary windings are 4800 turns and the secondary windings of 2000 turns. Why is an AC supply used? To produce an alternating EMF. Obviously, you have an alternating current, AC. An alternating current will produce an alternating EMF by V equals IR, Ohm's law. If this is, or sorry, this is, yes. No. V equals, V equals IR. Sorry, Ohm's law, right? So since you have an alternating I, this can go plus to minus to plus to minus, right? This is also going to go plus to minus to plus to minus, right? Because you're alternating both and they're directly proportional. So you produce an alternating EMF with an AC supply. Why is the core joining the primary and secondary windings made of iron? Now, iron is magnetic. Remember, iron is a magnetic material, ferromagnetic material. So why are we using it? To ensure magnetic linkage, because it is a conductive material. It keeps the linkage between the coils good. It keeps it steady. So we use iron, specifically iron, and they might tell you in one of the options soft iron. Always pick it. Soft iron. This is the actual thing that's being used, not just any regular iron. No, it has to be soft iron preferably. Okay, fill in the blanks. The output voltage from the transformer is 100 volts. Now, how do we know this? We have these formulas that I want you to memorize. N2 over N1 equals 2. I'll explain what N means. V2 over V1 equals 2. I1 over I2. Okay? Now, N is the number of turns. Or windings, whatever. Yeah, number of turns. V is the voltage. I is the current. Okay, now, and 2 is the secondary coil. So 2 means secondary and 1 means primary. Okay, now that we have all of this, we want voltage, right? And what do we have? We ask ourselves these questions, right? For this type of question. We want voltage, so we're already going to use V2 over V1 for something. With what, we don't know yet. And we need to have either current or number of turns. What do we have given in the question? We have the number of turns, 4800 turns and 2000 turns. So we're not going to use the current since we don't have it. So we're going to use N2 over N1 equals V2 over V1. So I'm going to write it down. N2 over N1 equals to V2 over V1. Okay. Let's see what we have given in the question. We have the primary coil has 4800 turns, so N1 equals to 4800, and secondary coil, the secondary windings, has 2000 turns, so N2 equals to 2000. Perfect. Now, if you also read before the question by a bit, you have the ideal transformers connected to a 20 hertz supply. This is the transformer. So you have the supply here, like this, and it's alternating. So we're gonna like this, and then it's drawn like this, and then this is the current here. This is the windings joined by the iron coil, all like this, secondary windings, and then it transfers like this. Okay, this sign means alternating. It's this sign, but I don't know how to draw it since it's vertically. Whatever, this is the structure, right? You can see that the supply here, this is the power supply. The power supply is connected to the primary coil. So, meaning that the primary coil will receive 240 volts, right? Because if the power supply is 240 volts, that means the primary coil will also receive 240 volts because it's directly connected, which means that V1 equals to 240 volts, right? So we have N2, we have N1, N2, N1, and we have V1. We need V2, all that's left. So we're just going to substitute, right? N2 is 2000, N1 is 4800, V2 is what we want to find, so I'll leave it as V2, and V1 is 240. Now, you do this on a calculator, or you can do 4800, you cross multiply. So 4800 V2 equals to 2000 times 240, which is 2000 times 240, 480,000 volts, right? So then you divide by 4800 on both sides. So V2 is equal to 100 volts. Right? Alternatively, most of you will probably solve this on an equation solver. Plus, part C is 100 volts. Perfect. Now, part D. The output frequency is 50 hertz. We were given that the ideal transformer is connected to a 50 hertz supply. We know nothing about frequency, because the hertz is the unit of frequency. In terms of transformers, we don't know anything about this, right? It wasn't in the book, it wasn't mentioned anyway. I think it might have been mentioned in the book once as it was conserved. And if you check it practically, yes, the frequency, the output frequency is equal to the input frequency, because why would it change? We're not dealing with anything that would lead to a change in frequency, right? Because an alternating current, right, this is given in an alternating current. The frequency will stay the same. This will be the graph of the power supply, right? So it will be like this. So this point here to this point here, where is it here? This will be 50 hertz. This is our frequency. Why would this change? There is no change that would lead to a change in frequency. We don't need to know why. It does change, so we can only say that the output frequency stays conserved at 50 hertz. Okay, question 7. An ideal transformer is connected to 120 volts AC main supply, so straight away V1. The primary coil has 960 turns, N1 equals to 960, and V1 equals to 120. What is the number of turns needed in the secondary coil to produce an output of 6 volts? This is V2 equals to 6 volts. Okay, we want the number of turns. Perfect, so it's going to be N2 over N1 equals to V2 over V1. We want N2, so we're not going to substitute anything for it. N2 over N1 is 960 equals V2 is 6 and V1 is 120. Okay, now again you solve on an equation solver or you cross multiply. 120 and 2 equals to 6 times 19, or 9 times 960 times 6, 160 times 6, 5760. You divide by 120 on both sides. V2, or sorry, N2 is equal to 48 turns. Okay, so that's our answer for part A. Now, what kind of transformer is this one? Step down. Why is it step down? Listen, there are cases. There are two cases. N2, if N2, the number of turns, N2 is greater than N1, then it is a step up transformer. Okay, if N1 is greater than N2, then it is step down. Right? If N2 is equal to N1, then why is it a transformer to begin with? We don't need to worry about N2 equals to N1. There is no equals to. Right? So keep these two in mind. Now, here, let's check how much turns we have. The primary coil, N1, has 960. The secondary coil, N2, has 48. Which is greater? N1. So, N1 is greater than N2, meaning that it is case 2, which is a step down transformer. Okay, question 8. What is it meant by describing a transformer as ideal? No energy dissipation, right? Because nothing is lost, everything is conserved. That's why it's ideal, 100% efficiency. Okay, an ideal transformer is used to operate at a normal brightness, a 12 volt 48 watt lamp from a 240 watt or 240 volt supply. Fill in the blanks. The current taken in by the lamp is blank amperes. Okay, we have the power of the lamp in watts, so P, and we have the voltage. So what formula relates power, voltage, and current? P equals IV. Again, these are from electricity. So we have the power, which is 48, equals to I, which is what we want to find, and 12 is our voltage, so it's going to be 12I. I is equal to 48 over 12. I is equal to 4 amperes. Okay, this is part A. Part B, or double I. The current in the primary of the transformer connected to one decimal place is 0.2 ampere. Okay, this is gonna be I1 over I2 equals to V2 over V1. Right? Now, you might be asking me, this is a lamp, there is no secondary coil, primary coil, whatever. No, what we're gonna assume here is, let me just clear this off, this part A working here. What we're gonna assume is the lamp is the second coil, or the second coil, yes. So we need to know what to do here, right? We have V2, we have I2, right? We have V1, we need I1, right? So we have all of this given, we just need to find I1. Now, it's going to be I1 over I2, which is 4, is equal to V2, which is 12, over V1, which is 240. So then you cross multiply again, 240 I1 is equal to 12 times 4, which is, I think, 48, yeah, 48. Divide the 48 by 240, so I1 is equal to 1 over 5, or 0.2 amperes, and this is your answer. Okay, question 8, or question 9, sorry. I don't know why it's stuck. Oh. Yeah, this is, I don't know where I am. Okay, there we go. Drag and drop the correct answers to complete the sentences below. A disturbance that travels through a medium or space from one location to another is called a pulse, not a wave. Not a wave. Okay, keep this in mind. A wave is a chain or series of pulses. One pulse, a pulse only, is a disturbance that travels through a medium or space from one location to another. The wave is shown in figure B, right? Because again, this is a pulse. This here, this is a pulse. You can see here, this is one pulse and these are two pulses. Since these are two pulses and a wave is a chain of pulses, right? So like this, This means that B is the wave because it is chains of two pulses. Okay, perfect. Question 10. A representation of a sound wave is shown below. This is the figure. When which regions is the air pressure maximum? Now, this is where this graph of pressure against just gonna say time of a wave comes in. So it's always gonna be like this. Okay, this is a very bad drawing, but yani it's gonna look like this. Actually, it's gonna, yeah, okay. At this point here, okay, the waves or the particles of the wave are as close as possible, right? They are compressed. So at this point, it's a compression. Okay, now this is at the highest pressure, maximal pressure. Okay, but at this point here, the particles are spread apart the most they can be. So the lowest pressure, right? This is gonna be lowest, and this here is gonna be highest. So at the lowest pressure, where the particles are spread apart the most, we call this a rarefaction. Okay, so in which regions is the air pressure maximal? Maximal means the highest pressure, referring to our graph. It is a compression. So when is it compression? It is a compression when it's a straight black bold line. So it's gonna be A and C and E because they're all straight bold lines. So ACE. Which regions is the air pressure minimal? So the lowest pressure. Going to our graph, it is at the rarefaction. The rarefaction is a dotted black line. So it's gonna be B and D because they're both dotted lines. And so it is B and D. Plus. Okay, that is question 10. Question 11. Sound waves are mechanical waves, as we said it in the previous question, and light waves are electromagnetic. Now, here are some differences between electromagnetic and mechanical waves. Electromagnetic waves do not need a medium to travel through, but mechanical waves, they do need a medium. That's first of all. And secondly, the waves, the mechanical waves, each mechanical wave has a different speed, right? Each of them travel at a different speed. However, all electromagnetic waves travel at the speed of light, 3 times 10 to the power of 8 meters per second, in vacuum. All have the same speed. That's what makes them electromagnetic, pretty much. So these are some features and properties of electromagnetic and mechanical waves. Okay, so sound waves are mechanical waves and light waves are electromagnetic. Question 12. A loudspeaker is creating sound waves in air. The diagram below shows the position of air particles at an instance of time as the sound wave propagates. Okay. This is actually going to help me explain compression and rarefaction. This point here, this like all of this here, this is compression. Okay, you can see here and like here, they are spread apart. So these are this, from what I can see at least, or sorry, these two are close together, so I wouldn't consider it. I'd consider it this place here. So let me just erase this box. They are the farthest apart here, and this. So this is what I would call a rarefaction. Just to help you further understand. Okay, sound is produced by a mechanical disturbance, so it's a mechanical wave. Yes, sound is defined as longitudinal. Yes, it is. And the loudspeaker vibrates. Air molecules in the same direction as the sound wave propagation. Yes, this is what makes it longitudinal. The vibrations of the molecules or the particles are in the same direction as the wave propagation. So the wave will propagate like this, for example, like this. The molecules vibrate also like this. They will both vibrate in the same direction. That's a longitudinal wave. Now, there's also the transverse wave. The transverse wave, the particles vibrate normal or perpendicular to the direction of the wave propagation, right? So the wave is gonna propagate like this. The molecules, now this is going to be in 2D, not 3D, a 3D diagram that makes it better, but the vibration of the air molecules in this case, if sound was transverse, which it isn't, would go like this. They are normal or perpendicular. This will be brought up later in the quiz, I think. Okay, question 13. a train of waves travels in a stretched spring at a rate of 2 waves per second, what is the period of this wave? Okay, this is the frequency. This right here is the frequency. Now, listen, there are two formulas for this. Frequency, or it's actually the same formula but different positioning. Frequency is 1 over the period. The period is denoted as t, and the period is 1 over the frequency. These are the two formulas you will be using in the question. So, since the frequency is 2 waves per second, so it's actually 2 hertz, the wave, or sorry, the period of the wave, t, is going to be 1 over 2, which is 0.5 seconds. Basically, what a period is, how much one wave travels, or sorry, like, how do I explain this? The period of the wave is how quickly a wave is, like, a pulse is completed. Yeah, pretty much how quickly a pulse is completed. So in this case, one pulse or one wave is 0.5 seconds. One wave of this. The time for one complete cycle of a musical note is 4 times 10 to the power of negative 3 seconds. So this is one note, right? This is the period. This is how much one note is in terms of seconds. This will help me further explain what a period is. What is the frequency? The frequency is 1 over the period. So you're going to put it on the calculator. 1 over 4 times 10 to the power of negative 3, which gives you 250 hertz. Now, a radio station broadcasts at a frequency of 100 megahertz. Megahertz, keep this in mind. M capital is mega, which is times 10 to the power of 6. What is the period of the electromagnetic waves it broadcasts? Now, the period, again, frequency is 1 over the period, so the period is 1 over the frequency, which means that the period is 1 over 100 times 10 to the power of 6. You do on your calculator, 1 over 100 times 10 to the power of 6 gives you 1 times 10 to the power of negative 8, or 10 times 10 to the power of negative 9. And remember, nano, n, is times 10 to the power of negative 9. So, this meaning that 1 times 10 to the power of negative 8 seconds, yes, is equal to 10 nanoseconds. So that's why we put 10 nanoseconds in the answer. Okay, question 14. So first what I would do here, I would draw the axes. So this would be my axis here, and this would be my midline. Okay, obviously it goes down as well. Now, which letter represents the amplitude of the wave? The amplitude is from the axis to the peak of the wave. Okay, in this case, look at point X. It goes from the axis, this would be time. It goes from the axis to the peak of the wave, which is, this would be displacement, the amplitude. So X is our amplitude. Which letter represents the period of the wave? This will actually help me explain what the period is. It is Z. Look, it is how much it takes for one wave to travel. As you can see here, this is one wave of sound, right? Let me just erase everything in this area so I can clear it up. Look at Z. Z is this. Z is denoting this. This is how much, this is one sound wave, right? This is one sound wave. Okay, now, so basically, a period is the time it takes for one sound wave to travel. This is, or one wave in general to travel. So, by our definition, what letter would represent the period? Z, right? Because we just said it is one wave of sound, in this case, in a certain time. So Z is our period. Question 15. A soft, low-pitched and high-pitched sounds travel A, B, C, and D are shown below. All waves are traveling through water. This is very important. All sound waves are traveling through water. Which sound wave travels the slowest? Speed of mechanical waves, okay, because this is sound, which is mechanical, does not depend on more so its frequency or pitch or amplitude or whatever. No, it depends on the medium it is traveling through. Okay, here in this case, they are all traveling through water. So no matter, say this, I also made wave E, okay? It is traveling like this, mashallah, huge wave. Doesn't matter, it's traveling at the same median as all of these. So all of these waves, A, B, C, D, E, will all travel at the same speed, because the speed of mechanical waves, not just sound, any mechanical wave, keep this in mind, not electromagnetic, just mechanical, they only depend on the medium of travel. That's their speed. Question 17 or 16, sorry. What happens to the amplitude of the pulses once they meet? It increases, yes, because as you can see, they're both, well, if we take this one positive, this side to be negative, they are both on the positive side. So this would actually go like this. So 1 second, they're traveling like this. Okay, then at the point of intersection, at the time of intersection, they would go like this, where you know that like the distance is, it's like technically like this, right? And then, so this is 1, this is step 1, this is stage 2, stage 3 would be that they continue along their path. So this wave here, this one will continue traveling like this, and this one here will continue traveling like this. Okay, this is superposition. I think that's what they call it. Yes, superposition. Okay, so here, since they're both positive, we'll call them positive, in this case positive and negative, remember, the amplitude will increase. This was, the cases I just described was for the positive case. Now, let's take that one, or both positive or both negative. That was for both of them. Let's take one was on the positive, like this, traveling, okay, and one was on the negative, like this, traveling. Okay, this would lead to nothing. This would like basically lead to this, which they will essentially cancel out if they're of the same magnitude. So they cancel out. We're assuming they are of the same magnitude, طبعا, in this case, leading to nothing being there. So essentially, this is what you're gonna have, something like this. Okay, and then it will continue on its way, where this one keeps traveling and this one keeps traveling. Okay, in this case, if they were both positive, let's take them. Obviously, there is no such thing as positive and negative here. So our amplitude will increase. They are both on the same side, let's say. Fadi claps his hands 5 meters from the flat window of a building. If Samir is inside the building, who will hear the clap? طبعا Fadi will always hear it, because he's the one who's clapping. Unless he's deaf, which I don't think he is if he's hearing it. And sound travels quickly, right? Sound travels quickly and it penetrates a lot. It goes through a lot. It has a large, it can travel a lot. So even if it's 5 meters, Samir can still hear it, because it's on a flat window anyway. If it's open, if the window's open, and because it's flat, we have to assume it is, sound will travel through the window onto Samir, and he will also hear it. However, Samir will hear it milliseconds or even nanoseconds after Fadi will. Samir will hear it later, not at the exact same time as Fadi did. So, question 18. Interference patterns occur when two pairs S1 and S2 produce coherent water waves as shown below. On which quantity does the interference patterns depend? Okay, so this depends on, first of all, only and primarily the wavelength. Okay, it does not depend on anything else. And part B, what happens when the waves or the wavelength of the water waves is shortened? Now, you might be asking me, how do they get closer together? Okay, say this is our water wave, like this. Actually, I'm gonna need to draw it fully. This is the current wavelength, right, from peak to peak. This is lambda. Lambda is the wavelength. However, and say this is another wave, right? They're intersecting, which causes the interference, whatever. But then you are shortening their wavelength. So it's gonna be like this. Or let me just draw it shorter. So it's gonna be like this. Look, the wavelength now is much shorter. Much shorter. So that means that if they intersect, look, they will get much closer together. Right? They will meet way closer than previously. If you increase their wavelength, they will spread apart. The interference patterns will spread apart. But here they're shortening them. So they will get closer together. Okay, question 19. Place a cardboard with 2 small slits separated by a small distance in front of a screen. Shine a monochromatic laser on the two slits and observe the screen in the dark room. A system of alternating bright and dark fringes are equidistant and parallel to the slits that are formed. What phenomenon is being experimented? The interference. We just showed it with the other question, right? Since these are the fringes, that means it's the intersections, right? It's the interference with each other. Okay, this is not diffraction. Please don't confuse it. I know people confuse it with diffraction. No, this is interference, which are very distinct apart. Okay. Which generator generates an alternating current of these two? It's going to be generator A. Just memorize it. It's going to be generator A. This will come up later. Okay. Which generator generates a current in one direction only? This is alternating current AC. One direction only means DC. So we need the DC generator, which is this, the illustration B. Okay, moving on. And by the way, just to help you know, if you have slip rings, it's AC. If you have split rings, split ring commutators or split rings, okay, these are split rings, right? This here in illustration A are slip rings. Keep this in mind. In generator B, it is split rings or split ring commutators. Same thing. But the point is, know the difference because they can help you identify which one. Slip rings are complete. As you can see, they are one complete circle. Okay, split rings, they're split down the middle. So that's how you know. If it's a split ring commutator, it's in illustration B, which is the DC. And if they are slip rings, they are alternating, which is in illustration A. Okay, this is a right-hand rule, but this can be memorized. I don't recommend you do, but essentially this is how you do it, right? I'll teach you the right-hand rule first. This, how do you say it? This magnetic field is facing away from you, right? Because this is the arrow, right? This is what crosses and dots mean. You can either have a cross or a dot, right? How do we know which is which? Look at an arrow. Okay, if it's at the tip of the arrow or the head, it's a cross, right? You're just continuing. But if it's at the end of it, it's a dot. So this is how we get the crosses and the dots. Now, since this is the cross of the arrow that's pointing towards you, that means the arrow is actually coming towards you, right? So this magnetic field is out of the plane into you. I think, yes. Like closer to you, yani it's facing you. That's the arrow. Okay, so then you have this thing going in. This is opposing it, right? By Lenz's law, this will oppose this. Okay, so what you're gonna do, you're gonna flip it. Bring your thumb for this right hand rule. You're always doing the opposite of this. Okay, since this is facing away from you or into the plane. Sorry, I think I mixed it up earlier. This is going into the plane. Okay, and this is going away from you. You bring your thumb towards you because again, Lenz's law is the opposite. Okay, so this is going away. This is the cross of the arrow. Okay, so this is the dot. We're gonna treat it, since it's gonna go as the opposite. Okay, we're gonna treat it as if there was a dot here. So then you're gonna bring it towards you. Bring your thumb to your face. Then curl your fingers. Okay, curling your fingers will get you a counterclockwise motion. So the direction of the current in the loop, according to Lenz's law, I don't know why it keeps doing that, I'm sorry. According to Lenz's law, this is Lenz's law, is counterclockwise. Keep this in mind. Now, if you're too lazy to do this right hand rule, there is a way to memorize it. If it's a cross, okay, there are two cases for both of them. If it's moving in, like the illustration we have, moving in, we're gonna have a counterclockwise motion. But if it's moving away, so like the arrow I'm gonna draw in blue, let me draw it in blue so you can distinctify it. It's moving away, which means that it's gonna be, let me just write it, moving, let's say moving out, that's fine. We call it clockwise motion. Okay, this is for when the magnetic field is across. For the dot, when it's a dot, okay, it's gonna be the opposite. So moving in is gonna be clockwise. Moving out is gonna be counterclockwise. You can memorize this, or you can apply the right hand rule for it, which is in my opinion much easier. But if you ever forget it, memorize this just in case. Honestly, memorize this just in case you forget it. You don't even need to memorize both. You memorize one of them and just remember the other is the opposite. So for this, I'd recommend memorizing the cross since it's applicable here. And just remember that the dot is the opposite of it. That's it. But obviously, preferably apply the right hand rule. Okay. A coil of wire 0.09 meters squared is placed, this is our area, is placed in a perpendicular magnetic field. So from the normal, angle from the normal, we'll call it theta, theta from the normal is equal to 0 degrees, right? Because it's placed perpendicular, the magnetic field is like this. And if it's placed normal, to it, it's here. This is our normal. It's placed perpendicular, it's on the normal, so there is no deviation from it. Okay, the magnetic field magnitude 0.5 Tesla. T is a Tesla. This increases to 0.6 Tesla in 3 seconds. This is our time. Okay, now how do we do this? This is an application of Faraday's law. The EMF, the induced EMF, denoted by Appleson, which is like an A in Arabic or an E with the like a curve, I don't know, is negative d phi, or sorry, let me draw it properly, d phi over dt. Now d, if you don't know what that means, it's just delta phi over delta t, change in time, and the change in phi is the flux, the magnetic field, the flux of the magnetic field, so, or the change in it, sorry. So phi, let's find the delta phi, right? Delta phi is going to be phi 2 minus phi 1. Now you might be asking me, how do I calculate phi? Phi has a formula. Phi is equal to BA cosine theta, where B is the magnetic field, A is the area, theta is the angle of normal, whatever, from normal. Okay, so let's find phi 2 first. Phi 2 is so this is B1 here. 0.5 Tesla is B1. Okay, 0.6 Tesla is B2, right? So we're gonna use B2. So it's gonna be 0.6 times, the area was constant, 0.09 times cosine 0, which gives me 0.6 times 0.09 times cosine 0, which gives me 0.054. Okay, phi 1, let's find phi 1 now. Phi 1 is 0.5, because remember, it's B1 times the area, 0.09 times cosine theta, which gives me 0.5 times 0.09 times cosine 0, which is 0.045. Okay, now we want to find delta phi, which is phi 2 minus phi 1. So delta phi, or d phi, is equal to 0.054 minus 0.045 equals to 0.054 minus 0.045, 0.09. 0.009, sorry, let me write it down, 0.009. Okay, now let me erase this because it's getting very annoying. This is d phi, but remember, Faraday's law is negative d phi, or sorry, oh wait, no, it is d phi by dt. Lenz's law is negative d phi by dt, long story. So why does it keep doing this? Equals to d phi, which is 0.009 over dt. dt is 3 seconds, it's the change in time, over 3, which gives me 0.003 volts. Okay, now that we have this, what do we do here essentially? This is our answer, but in the answer key it says it's different. I don't think you guys noticed, maybe you did, good job. It is millivolts, MV. So you multiply this by 10 to the, by 1000, sorry, by 10 to the power of 3, same thing, gives you 3 millivolts, and this is your answer. Now I think they should accept negative 3 as well, لأنه it is technically كمان negative d phi over dt بس I'm not sure. They don't accept it. Yeah, okay, it's fine because that's Lenz's law بس expressed mathematically. You don't need to know though. For all you need to know is Faraday's law is negative d phi by dt, or I did the negative again. I'm used to having it negative. This is why you read the book, by the way. So, okay, question 23. Which of the following statements are true about the simple AC generator? Why does it keep doing this? Okay, remember that the AC generator is the current is removed via twin ring commutator. Okay, now remember how I said slip ring? As twin ring is another name. It's the same thing. Slip ring, twin ring, both the same. An AC generator can either contain a permanent magnet or an electromagnet. This is correct. And an AC generator can either contain slip ring or split ring. This is where that note I told you earlier comes in, because it can be a slip ring, not a split ring. This is DC, so this is incorrect. If the loop of the generator moves uniformly, the current generated varies according to a sine function. Yes, because it's an AC current. And if you forgot the graph of the AC current, it is essentially y equals sine x. This is the AC. Okay. Question 24. This is the parts of a transformer. So I'm not gonna start with the first one. I'm gonna start with the middle one, the soft iron core. Or yeah, so the soft iron core, remember how I told you it's ferromagnetic. It's a magnetic material that conducts that's not really, I think, conducts magnetism, but you know what I mean. That ensures good magnetism. So this is where the soft iron core comes in, because it links the magnetic field of the primary coil with the magnetic field of the secondary coil. It links them together for the transformer to actually work. This is why we use the soft iron core. Helps in generating an alternating magnetic field. Yes, because how are you gonna get a magnetic field into the secondary coil, right? Secondary coil, which is inducing an EMF, which is I'll get into now, without having an alternating magnetic field in the primary coil. It won't make sense. Yani you need magnetism to induce EMF, to induce current, right? So without a magnetic field, without an alternating magnetic field, keep this in mind, you won't have an EMF to induce, which is like essentially no point of the transformer then. So keep this in mind. The primary coil will induce or generate the alternating magnetic field, which in effect leads to an induced EMF in the secondary coil, which is why I wanted to start with the middle one first, because it links the magnetic coil, that links the magnetic field of the primary coil all the way to the secondary coil, leading to an induced EMF. So question 25. Transformer has 760 turns in the primary coil and 100 turns in the secondary coil. Based on the number of coils, it is a step-down transformer. Again, this is an application N2. If it's greater than N1, step up. I'm going to write SU. N1 greater than N2, step down. See here, N1 is greater than N2. Remember, N1 is 760, N2 is 100. So, N1 is greater than N2, meaning it's a step-down transformer. Question 26. Okay. The amount of loss in order to decrease energy of loss power transmission from the power plant to the grid, certain measures must be taken, drag and drop. The amount of loss in the energy of the wire is proportional to the square of the current in the wire. Remember why? If you forgot, power, which is power is I squared R. Remember? Which is why we get P equals to IV. But not relevant now. We don't need this. P equals I squared R. So the energy lost is proportional to the square of the current. Okay, this will be important later. In order to decrease these losses, step-up transformers are used, because again, you're trying to get more out of what you have. You're trying to get more voltage, like get more energy. So as a result, the grid transports at high voltages and low current. Why? First of all, remember, to minimize energy losses, since we're given that the amount of energy loss is proportional to the square of the current, so we're gonna lose a lot of energy if we have a lot of current. So we're gonna minimize the current, right? How do we minimize current? So this is why we have low current. How do we minimize current? Remember, V equals to IR. Now, I and R are inversely proportional because obviously the more resistance you have, less electrons can flow, which is obviously the definition of a current. The current is a flow of electrons. Now, since you have a low current, how do you achieve this low current, right? You're going to have a really high resistance. Since you want to stop, you really like you want to stop essentially very low currents, right? Like you're trying to get the current to be 0.0001 to maximize it, yani. So you're gonna have a very, very large value of resistance to stop this current from flowing through, because you can't, if you're inputting like 240 volts in as a primary coil, you're gonna have a lot of current. So you're gonna need a really high resistance to stop this. Okay, which is why we will have very low current. Okay, and also this can also explain V equals, this can also explain V equals IR for this. Since you're gonna have a very large value of the resistance, and the resistance and the voltage are directly proportional, as resistance increases, voltage will increase when current is constant, obviously. So you're gonna have a high voltage because you're gonna have a high resistance, meaning that the electricity will be transported at high voltages and at low currents. Okay, question 27. This is a much better drawing of the transformer than what I drew. Here you're gonna have a power supply here drawn like this. This is the current, and this is where the electricity will travel. Okay, so the peak EMF is 48 and 240 volts respectively. So the primary coil has 48 volts, so V1 is 48 volts, V2 is 240 volts. What is the number of turns N2 over N1 equals to V2 over V1? Now you might be asking me, where's N1 or N2? We didn't read here, but that's 60 turns in the primary coil, so N1 equals to 60. Now we need N2, so N2 over 60 is equal to 240 over 48. You know how to do this by now, so I'm just going to use my equation solver because I explained it 50 times. X over 60 is equal to 240 over 48. So X or N2 will give me 300 on my calculator, which is the correct answer. Okay. The current in the primary coil is 4 amperes, so I1 is equal to 4 amperes. And the current in the secondary coil, I2, is 0.72 amperes. What is the input power? Okay. Remember, P equals to IV. We have V given above. Let's copy it down. V is here. I'll just write it. So V1 is 48 volts, V2 is 240 volts, and I1 is 4 amperes, I2 is 0.72 amperes. Okay, now we're gonna use I1 over I2. Keep this in mind, not I2 over I1. The current is the only exception because it's inversely proportional, remember? Equals to, so this is gonna equal V2 over V1, right? So I1 is 4, I2 is 0.72, or sorry, we don't need this, we don't need to use this, but yeah, no, you don't need to use this, my bad, I didn't read ahead. What is the input power? Okay, P equals IV, so input power means I1 V1, so the power is 4 times I1 is 4 and V1 is 48, 4 times 48, which gives you 4 times 48, 192 watts of power. What's the output power? The output power is I2 V2 or V2 I2, it's fine. So this equals to 240 times 0.72, right? This is what we have given. So 240 times 0.72 equals 172.8. You round it to 173 watts. Okay, what is the efficiency? The efficiency formula is power out, the output power, over the input power times 100. This is efficiency. I'm not gonna write, I don't have space to write it down. So the output power was 173. We found it here. The input power is 192 times 100. This gives you a value of 90%. Let me just make sure. Yes, this gives you 90. Okay. Question 28. The table below lists the functions of the fuse and circuit breaker. Use the drag and drop the correct terms from the box below. Protects people from accidental electrocution based on the principle of the electromagnet. This is called the earth leakage circuit breaker. Please keep this in mind. Now, protects from overcurrent. These are all how to prevent dangers in electricity. Protects from overcurrent by melting down. When you see melting down, straight away write fuse. Okay, because this is how the fuse protects. It melts down, which stops the current from flowing. Protects overcurrent, should not be replaced after the event of an overcurrent. It is called the electromechanical circuit breaker. Please keep all of these in mind. These are very important. This is like a fairly new concept. You don't see this in any CA quizzes before. So essentially, just to recap, if it's protecting people from accidental electrocution based on the principles of the electromagnet, if you have electromagnet and accidental electrocution, it is earth leakage circuit breaker. If it's melting down, it's going to be fuse. If it should not be replaced, it is electromechanical circuit breaker. Okay, question 29. A 0.8 kilowatt washing machine works on a 220 volt mains supply. The current flowing is 3.6 amperes. Keep this in mind. Which of the following fuse is most suitable? 4 amperes. Now, for this, you always want to go over the value they give you. You always want to go over. However, you also want to get as close as possible to this value. For example, say we have 4 ampere fuse here. I don't know why it keeps doing this. You have 4 ampere fuse here, 4 ampere here, okay, fuse, and one of the options, this option. However, also on the choice, say they gave me 3.7 ampere fuse. I would go for the 3.7 ampere fuse because it's over 3.6 and it is closer than 4. You always want to go over and closest. Okay, question 30. Complete the following table to state whether a charge in each case experiences magnetic force. A charge that is stationary, since it's stationary, nothing is happening, no force. Charge moving, it is moving, and it's an angle of 30 degrees with the magnetic field. It experiences a force. But here, it's moving in the opposite direction, so no force. Okay, because this is the field here, and this is the particle. Where will be the force attracted? It's not cutting it. If it was like here, so let's take case 2. Say this is moving at an angle of 30 degrees like this. This would be an opposite story. This is gonna experience a force, but this isn't gonna experience a force. This case here will not experience a force since it's moving away from the magnetic field. So since this doesn't want to load, I'll just 1 second. Okay, my bad. Just have to do something. So the peak current in an AC current is 20 milliamperes. Fill in the blank. The RMS current to 1 decimal place is 14 milliamperes. Okay, listen. RMS anything really, because they can also ask you the RMS voltage. RMS, or this is root median square. Okay, this is what RMS stands for. They might just ask you, is the peak value. So in this case, it's current, right? So we're gonna say IRMS, and it could be voltage. It has been asked before. So in this case, it's current, but keep in mind that it can be voltage. The voltage is the same formula, but swap I with V. Here, IRMS is equal to the peak current, so I peak over radical 2. Okay. So now, what we're gonna do is apply the formula. IRMS is equal to 20 over radical 2 equals to 20 over radical 2, 14.1 milliamperes. Okay, here I don't know why they did it. They said to 1 decimal place is 14 milliamperes, but 14.1 was accepted. It should be 14.1. They shouldn't accept 14 because they did say to 1 decimal place. But in the exam, put it to 1 decimal place if they tell you to. Otherwise, put it to the nearest whole number. So yes, it is going to be 14.1, and that is your answer. Let me just make sure it was actually accepted. 14.1. Yes. Okay, question 32. This here is a DC generator. Okay, the DC generator, how do you know it has split? Keep this in mind. I can't keep reminding you guys, but because people do make mistakes. Split rings or split ring commutator. Now, since it's a generator and not a motor, this will be the value, or this will be the graph of the DC generator. Because again, how do you know? It's common sense really, because it's rotating, right? There is gonna be a change in current like this. Because in the end you have a rotation, you still have a change in magnetic field. Due to the rotation, you're gonna have a change in flux leading to a change in current. But however, this current will always be positive, and it will never alternate like a sine wave like an AC generator does. Now, they might ask you the graph of a DC motor, not generator, motor. The motor is like this. This is I, this is T. It's just a straight line. So always just keep those two in your mind. Okay, the efficiency of the transformer. This is again efficiency is output power over input power times 100. So let's find out. We can do this all in one step. Remember, P equals to IV. So the output power, or let's say P2 is gonna be I2 V2. Okay, so this is actually going to be I2 V2 over I1 V1 times 100. Just straight away, so we can do it on a calculator much faster. So let's erase everything else and keep this. Efficiency equals to V2 I2 over V1 I1 times 100. Okay, so what the primary coil is always 1, whatever it is, and the secondary coil is always 2. So I1 is 2.2 and V1 is 9 ohms, or 9 volts. So efficiency is equal to, and obviously secondary I2 V2, whatever, 162 milliampere. Keep this in mind. Look, we have milliampere here and we have ampere here. So we're gonna do times 10 to the power of -3 to change this to ampere. So this is actually going to be 162 times 10 to the power of -3 ampere, which is going to equal to 0.162 ampere. So let's just write it down. 0.162 times 110, because 110 was given as V2, and 2.2 times 9 times 100, all of this. Okay, do this all on a fraction in one step. 0.162 times 110 over 2.2 times 9 times 100. You will get 90%. Now, you can find the power out alone, so P out is going to give you 0.162 times 110, which will equal to 0.162 times 110, which will give you 17.82. Okay, and input power is going to be 2.2 times 9, which gives you 19.8. Okay, so you're gonna do 17.82 over 19.8 times 100, which equals to what is supposed to be 90%. Let me just make sure. Yes, 90%. So, and if you don't want to do it all in one step on a calculator, you can find each of them and then divide. But why would you? I don't know. Okay. A water wave can be generated by continuously tapping on the water surface shown below. Continuously tapping. One tap, if you remember, is equal to the pulse. This is one pulse. I wrote pulse. Nice one. Pulse. I almost did it again. Okay, pulse. So continuously tapping is going to be a chain of pulses. What does a chain of pulses do? It leads to a wave. So Waves or vibrations, because again you're tapping, which leads to water molecules vibrating, as you can see here. They transfer energy from place to place without matter being transferred. You don't transfer matter here. Waves, remember, they transfer energy with no matter leaving them. Question 35. Describe compression rarefaction from what I'm saying. Okay. So, row A, rarefaction, where particles of the medium are spread out, right? We told you this because they are like this. This would be here, for example, this would be rarefaction. Okay, now row B, compression, where particles of the medium are closer together, like this. This is a compression. Okay, I already explained this previously. Now, this graph under it, I also explained previously, but it's fine. We can explain it again. Which point represents description in row A? Description in row A is a rarefaction. Rarefaction means the lowest pressure. If you remember, this is our graph. Right? This is compression. This here is rarefaction. And this should be, keep this in mind, this should be a pressure to time graph. Okay? Now, the compression is at the peak of the curve. So, it's at x in this case. The compression is at x. The rarefaction is at the trough of the curve, which in this case is z. So here is going to be rarefaction. Okay, so which point is represents the description in row A? Again, row A is rarefaction. We said that rarefaction is at the trough of the curve, which is at z. Okay. Which point represents the description in row B? Row B is a compression. Compression where is the highest atmospheric pressure, in general, which is at point X at the peak of the curve. So X is the answer to part C. 37 or 36. Match each term to its description. Frequency. Frequency is the number of cycles completed per second. Okay. Speed, I don't think it needs an explanation. The distance traveled per unit of time. And wavelength is lambda. Okay. This is what wavelength is. So let me actually just draw a graph. I don't know why I keep drawing it like this. Whatever. Okay. I'll draw it one final time. Okay, this is good. So assume these two are the same height. I'm not a very good drawer. Okay, so this will be our peak here. Okay, from peak to peak, the distance between peak to peak is what we call lambda, which is the wavelength. Okay, so we match wavelength to the length of the wave from one peak to the next. I mean, it's in the given. Yani, wavelength, the length of a wave. That's pretty much it. Yani, this question is very easy. Amplitude is the maximum displacement from a particle at its rest position. So, for example, say we have this curve here. This here, from the axis to the peak of the curve, is what we call the amplitude. Okay, this is our amplitude. It is and again, this is a displacement here. This is a displacement time graph. Question 37. Okay. Consider 4 grams below plotted using the same scale. Which graph is the loudest? Loudest. I'm gonna ignore these lines now, man. Loudest means the highest amplitude. Okay, so we're gonna need to look for a point with the highest amplitude. As you can see here, this amplitude is very small. This amplitude is a bit bigger, but it's not big enough. This amplitude is very, very small. This amplitude is actually very big. This amplitude is very nice. So B is the loudest sound because it has the highest amplitude. Okay, which graph has the highest pitch? Highest pitch. What did I write? Okay, as you can tell, I'm not very good at English. Highest pitch means highest frequency. Okay, so we need the graph that occurs the most in the same time span. Here, this graph doesn't even complete one lap, right? This isn't one wave. It's a very slow wave. So this actually curve C has the lowest pitch. Okay. A doesn't complete it fully yet, but it's almost there. Okay. B doesn't complete it again. Here, not only does D complete one time, as you can see, it completes it 2, 3. It completes it 3 times. This is the highest frequency. So D has the highest frequency, meaning that it has the highest pitch. Okay. So those are our answers. Question 38. Reflection of a wave, since it's reflection, obviously it can't pass through the medium. This is wrong. And since it's going to travel like this, it's going to reflect like that. Look, this is obviously how the reflections can actually, yeah, it's not very accurate, and no reflection has to equal each other. So like this, but then something like this. I don't know. It's going to reflect weirdly. But you know what I mean. The angle has to be equal. This is obviously wrong. I don't know how will it bounce back. Doesn't really make sense. Right? So this is incorrect. This only happens, I think, when it's perpendicular exactly. Here, as you can tell, the plane, perpendicular to the plane, like perpendicular to it. As you can see here, this isn't perpendicular, right? Because this isn't a 90-degree angle. So this will not happen. And it cannot bounce like this logically, leaving the only answer to be A. Okay. Question 39. Almost done. A ripple tank shuttle, 2 holes of water, deep and shallow, and oscillators use that one. Okay. Drag and drop the correct terms. Okay, this is normal. This is deep water here. Right, because that can't be seen. The property in deep water. Now, listen, and this is something you should memorize. Deep and shallow water properties of waves. In deep water and shallow water, the frequency stays the same. Okay, and I'm gonna leave this to the end. Actually, I'm gonna leave the middle one to the end. The wave speed in deep water is greater than the shallow in terms of speed. Okay, now why did I leave this one to the end? Because if you remember the formula, V equals F lambda to find the speed of a wave, right? Since we have the same frequency, but we somehow have a greater wave speed. So the frequency is the constant. So let me, that I erased the wrong thing. Frequency is constant, so this is gone. And we have a greater wave speed. So that means we're gonna have a greater lambda in the deep water, right? By the formula. Because we have a greater wave speed and we have the same frequency. So frequency isn't the factor we're changing here, right? Somehow we're getting a greater wave speed with the same frequency. Which leaves the only factor to change is lambda. Lambda is the wavelength. So that means since the wave speed in deep water is greater than in shallow water, the wavelength in deep water will also be greater than in shallow water with the same frequency in both. Okay, this is a classic example of diffraction. It will actually diffract like this. Okay, it's very inaccurate, but keep this in mind. This is diffraction on a narrow gap. Okay, if this was a wide gap, because they might ask this, you never know. If this was a wide gap, it would be closer to being like rectangular, as you can see. Okay, so this is something you need to know. This is just an example of diffraction. The diagram below, this is another example of diffraction. Which factors affect the amount of diffraction? Width of the gap, obviously. If it's narrow or wide, I just said this. If it's narrow, it's going to diffract circularly. If it's wide, it's going to diffract closer like a rectangle. So it's the width and the wavelength of the water waves. It depends on the length. Essentially, diffraction is all factors of length. Density and type have nothing to do with length, right? And the amplitude isn't the length. It's more of a height. So leaving the width and the wavelength to be the correct answers. A wave in which the displacement of particles is along the same direction is called longitudinal wave. I explained this, but I'll explain it again. So, say the wave travels like this. Okay, this is one wave. The particles will displace in this direction. The particles go like this. However, the particles, say we had another wave like this. Okay, and the particles displaced like this. This is inaccurate obviously because it's 2D. This would, but as you can see here, they're perpendicular to each other. And this would be inaccurate, but this is gonna have a 90-degree angle with the wave. They would be normal, they'd be perpendicular to each other. This would lead to a transverse wave. So basically, the definition of a transverse wave is the exact same wording as this. The only difference being is along the same direction, no, along is perpendicular to. This is what you swap with this, and this would be the transverse waves definition. However, they're not asking for this. A transverse or longitudinal wave is the wave in which the displacement of the particles, so the travel of the particles, is in the same direction as the direction of the propagation of the wave. Calculate the speed of the wave. The speed of the wave, we always use v equals f lambda. Okay, we have we want v, we have f and lambda. V is equal to 1200. This is the frequency, 1200 times. Now this is where a lot of you will go wrong, because here it's 25 centimeters. They want it in meter per second. So what we're gonna do, we're gonna change this to meters. This is gonna be 0.25 meters times 0.25, which gives me 1200 times 0.25, 300 meters per second, and this is my answer. Okay, for the final question, this is I explained this previously. It's when there's one positive and one negative. Okay, like assume that these are the directions at point A, right? Remember I said they will essentially cancel out if they're the same wavelength. Here we're assuming they are, yani, but sometimes they aren't, and in the question they'll tell you if they want you to actually find it. Here they just want to know the phenomenon. This is called destructive interference. Okay, this is destructive because it's gonna cancel out, right? It's gonna like cancel the effect of each one. It's gonna decrease it. Okay, so you're destroying something. However, the other one, where they are both positive or both negative, again, both work like this or like this, whatever. I'm gonna take one of the cases. I'm gonna take the negative one this time. When they will meet, okay, so they are going like this. This will be constructive interference. Okay, not destructive, constructive. Here, however, it's one on their own opposite sides, right? So they are essentially gonna try to cancel out each other's effect. So they're destroying each other. This is why we call it a destructive interference, and this is the phenomena that occurs at point A. Okay, this was the end of the quiz. Good luck everyone. Physics periodic will be uploaded soon. Most of the quizzes are already out, but there are 2 sections I have yet to upload. They will be either out today or tomorrow. Yalla, good luck guys.